Welcome to Unacademy, the largest online e-learning platform. Welcome to Unacademy semester exams. Today, we are starting with Network Analysis and Transmission Lines crash course. Network Analysis and Transmission Lines crash course. So in this, we'll be discussing about the network analysis as well as the transmission line concepts. So welcome to Network Analysis and Transmission Lines. And today our topic is magnetic circuits. Today our topic is of magnetic circuits. Before that, let me tell you about myself. I am Vai Shravan Kumar, having 7 plus years of teaching experience and mentored more than 5K students for GATE and engineering services and cracked GATE. Welcome Srilata, good evening, and Chandrakiran, good evening. Shivakumar, good evening. Welcome to Network Analysis and Transmission Lines crash course. Also, let me tell you about an academy learning app installation procedure. So just need to type an academy learning app in Google Play Store. You'll have this app and you can click on this install. Good evening Krishna Chari. Good evening Soumya. When you click on this install, you'll get this screen and you can opt for GATE and engineering services and click on this plus, so that you'll get the get subscription button. Once you do that, you'll have two options. Either you can go for plus subscription or iconic subscription. You'll get a dedicated mentor for your preparation in iconic subscription, and you can also use my code as YSK10 to get the maximum discount. And you can click on this proceed to pay. Once you click on this proceed to pay, you have options like debit card, credit card, EMI, UPI, wallets, net banking. Using any of these platforms, you can get subscription to the an academy. You can get subscription to an academy. So, an academy has brought Evolve for GATE 2022 electrical batch A in English and Hindi starts on 21st of December. We have the India's top educators Ankit Goyal sir, Ajay Gupta sir, Hafiz sir, and BV Reddy sir, and Suresh Vyasar sir. We have top educators for electrical batch A, and it is about to start from 21st of December. So everybody can make use of this good opportunity that you have. And let me start for today's topic. So today's topics are magnetic circuits introduction. We'll just introduce what magnetic circuits are, and we'll see some basic definitions of magnetic circuits. Then we'll get into details of the subject. So let me first tell you what is a magnetic circuit, and what is a magnet and what are its properties. So what is a magnet, and let's see what are its properties. Let us see what is a magnet and what are its properties. So first, what is a magnet? A magnet is a piece of solid body which possess the property of which possess the property of attracting or repulsion. So this is just a magnet. And what are the properties of it? You have a magnet like this. It has a north and south pole. So what are the properties of this magnet then? So if you are looking at the properties of this magnet, let us see what are the properties. What are the properties of these magnets? So if you look at these properties of the magnets, the first one is when a magnet is placed near any iron pieces, it attracts them. And most of the accumulation of these iron pieces accumulate most of these accumulate at the most of these gets accumulated at the corners. and those points are called as poles, and those points where the maximum accumulation takes place, Jayant, good evening, takes place is called as poles, and at the center there will be a less accumulation. So these points where you get maximum accumulation are called as poles, and they are named as north pole and south pole. As you know, it is north and south pole, you have two poles. Now let's also look at the second property. The second property of magnetic circuits. Welcome Jayant, good evening. When a magnet is suspended freely, when you suspend a magnet freely, when a magnet is suspended freely, it aligns itself in north and south directions. In in north and south directions. That means if you have a magnet, let's say you have a magnet like this, and if you just try to suspend it, then it will align itself in north as well as south directions. Karthik, good evening. Simi, good evening. So it aligns itself in the north and south directions. So this is the second property of magnetic circuits. Now coming to the third property. Now when a magnet is placed near an iron piece or a steel piece, when a magnet is placed near iron or steel piece, what happens is its property gets transferred. Its property gets transferred to this material, magnetic material, and this property is called as magnetic induction. And this process of transfer of this process of transfer of this magnetic property is called as Chandrakiran. Super explanation. Thank you, Chandrakiran. Now let's look at this. Let's once again see the first property. What is the first property? The first property is when a magnet is placed near any iron piece, it attracts them, it attracts them, and the most of the accumulation will occur at some points, and those are called as poles. And at the center, it will have less accumulation, and I have shown this. Coming to the second one, when a magnet is suspended freely, it aligns itself in the north and south directions. And the third property is when a magnet is placed near an iron or steel piece, the property of this attraction property will get induced in these materials which are placed. That property is called as the property of induction or transfer of this attraction property in the other materials placed nearby it is called as the magnetic induction. Now let us see the fourth property. Now let us see the fourth property. If a magnet is broken into two pieces, if a magnet is broken into two pieces, still it will have still both. So let's say you have one magnet here and it has north and south poles, and you are trying to break it. This will become two magnets, and which also will have north and south pole, which also will have north and south poles. That means any magnet, if it is broken or if it is a single one, it will also have north and south poles. That means two independent. It will also have, and this will also have that. Also, as I told you in the previous point, some materials show the property of attraction when even after removal of magnetism. That is called as retentivity. That is called as retentivity. Retentivity. Now we have seen retentivity. What is retentivity? It is a property of a magnetic material to retain magnetism. That is property of a material to retain magnetism even after removal of it is called as retentivity. It is called as retentivity. Now let's look at some basic laws of magnetism. What are the basic laws of magnetism? Laws of magnetism. What are the laws of magnetism? Let us look at these magnetism laws. Let us look at the laws of magnetism. Let us look at the laws of magnetism. So we have seen what are the properties, what is a magnet and what are the properties of a magnet. Now let's look at the laws of magnetism. So the first law states that like magnetic poles which are like and which are unlike. There are two kinds. Suppose you have a magnet, this is magnet 1 which has north pole and south pole. You have another magnet which also has a north pole and south pole. So if these two are placed adjacent to each other, that means these are called as unlike poles. Now when you have like poles, they will repel. When you have like poles repel and unlike poles attract. So similarly, if you have two magnets placed adjacent to each other, this is north pole, this is south pole, and this is south pole, this is north pole. Here there are like poles. Now if you observe these, what is going to happen is here they will attract, here they will repel. This is the first property or first law of magnetism. First law of magnetism is like poles. So we can say like poles repel. Thank you, Chandrakiran. And unlike poles attract. Like poles repel and unlike poles attract. So this is the first law of magnetism. Now let us look at the second law of magnetism. It was proposed by Coulomb. This was proposed by Coulomb, Coulomb. Coulomb's law, this is called as Coulomb's law. It states that the force of attraction or repulsion between any two bodies is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. It states that the force of attraction or repulsion between any two bodies is directly proportional to is directly proportional to is directly proportional to product of mass and inversely proportional to square of the distance between them. Square of the distance. And the units of force are newtons. You'll replace this force proportionality constant and you can write 1 by 4 pi epsilon naught m1 m2 by d square, or it is also written as r square. So these are the units of force, newtons. Ravi Kumar, good presentation. Thank you, Ravi Kumar. So we have seen the two basic laws of magnetism. One is magnetic like poles repel and unlike poles attract. like poles repel and unlike poles attract, and the other one is the force of attraction or repulsion between the two bodies is the force exerted by the two bodies or one pole on the other, nothing but the force exerted by one pole on other is directly proportional to the mass of product of their, here m is their pole strength. It is directly proportional to the product of their pole strength. It is directly proportional to their product of their pole strength. Raju, good evening. Welcome to network analysis and transmission lines. It is directly proportional to the product of their pole strength here in this case of magnets, and inversely proportional to the square of the distance between them, and inversely proportional to the square of the distance between them. So you can also replace this f, you can also write f is equal to, instead of writing constant you can write k into m1 m2 pole strength by d square. In general, Coulomb's law is defined as the force of attraction or repulsion is between any two charges or any two poles is directly proportional to the product of the masses. Here we are taking, because it is a magnetic circuit, here we are taking the pole strength, m1 m2 are the pole strengths. So you can write it is directly proportional to the product of the pole strength and inversely proportional to the square of the distance between them. Now let us see what is magnetic field and what are magnetic lines of force. What is magnetic field and what are magnetic lines of force? So let us write what is, we'll see what is magnetic field. What is magnetic field? It is the region around a magnet, region around a magnet where its effect can be felt, where its effect can be felt, where its effect can be felt. That means you have a magnet. Let us take this as north pole and this as south pole. And if you see, if you see, let's say you have placed a magnet here, we have placed a iron piece here, and you are able to sense the effect of this. Either it is attracting or it is repelling, or it is attracting. Now, if you place it here, it may not get attracted or repelled, because till this point, let us say this is the region around a magnet where you can feel. In this region, wherever you place it, place a piece of iron, you will feel the effect. So this region around a magnet where you can feel the effect. Sir, how many questions may be expected from this topic? Karthik Jilla. Yeah, you can expect basic definitions. If you are given the short answers, you'll definitely expect one question from this, and you can also expect a long question based on the formulas that we'll be discussing very soon. So this is magnetic field. Thank you, Karthik. Now we'll discuss what are magnetic field lines. What are field lines, or they are also called as flux lines? Field lines or flux lines. What are field lines and what are flux lines? Or they are not denoted by flux, pi or lambda flux linkage. So if you see, what are field lines or the flux lines? The lines of force, they are the lines of force, the lines of force around a magnet. The lines of force around a magnet are called field lines or flux lines. And these are imaginary lines. They are imaginary lines around a magnet. They are imaginary lines around a magnet. They are the imaginary lines around a magnet. And these were introduced by Michael Faraday. These were introduced by Michael Faraday. They are the imaginary lines. Why did these get as magnetic flux lines or field lines? To get visualization of, these were proposed by Michael Faraday to get the visualization of distribution of flux around a magnet. To get the visualization of distribution of flux around a magnet, it is these are taken. So let us take one magnet here. If this is a magnet, the lines of force around this, let us consider one line of force, then another line of force, and there is another line of force, and you can also consider the line of force. Here if you can see these lines of force around a magnet, and the lines of force are always from north pole to south pole outside the magnet, and they are south pole to north pole inside the magnet. So these flux lines, which are imaginary lines around a magnet, are called as, these flux lines around a magnet are called as the field lines. The imaginary lines around the magnet are called as flux lines or field lines. So this is the second one. So we have seen what is a magnetic field, and then we have seen what are magnetic flux lines. Now let us see what are these properties. Now let us see what are the properties of lines of force. These are called as field lines, flux lines, or lines of force. What are the properties of lines of force? The lines of force are always originating, they will always originate at north pole and terminate on south pole, external to the magnet, external to the magnet. That is the one property of flux lines, lines of force. Hi Saidulu, welcome to network analysis and transmission lines. Now the second one is the lines, each line forms a closed path. Each line forms a closed path. Each line will form a closed path. Each line will form a closed path. Now let's take this to the next slide and write all the properties. So the first property is they originate at the north pole and terminate on the south pole. Each lines of force is a closed path. Now let us take the third one. So these are the two properties, and let me write the third property. So the third property of the lines of force will never intersect. The lines of force will never intersect. These lines of force that you have around a magnet will never intersect. These lines of force around a magnet will never intersect. And these lines of force are always, the lines of force are always parallel to each other. These lines of force are always parallel to each other in the same direction. They are parallel to each other in same direction. And they repel each other also. They are parallel to each other and in the same direction. They travel in the same direction and also repel each other. Alright, so the next is the magnetic lines of force always prefer, magnetic lines of force always prefer a path, always prefer a path with, which is offering, prefer a path offering low opposition, and this opposition, low opposition, and this opposition is called as reluctance, and this opposition is called as reluctance. What is that? Now we'll see what is reluctance. What is reluctance? What is reluctance? The opposition offered by is the opposition offered by material to flow of lines of force is called reluctance. It is denoted by S. It is denoted by S. That is denoted by S. Now, air has maximum or more reluctance as compared to materials like iron, steel, etc., which have low reluctance. Which have low reluctance. So now we have seen, let me revise all the things that we have studied. So we have seen what is a magnet and what are its properties. The property: when a magnet is placed near iron piece, it attracts and accumulates more at the poles, and at the center it accumulates less. Now, when a magnet is suspended freely, it aligns itself in the north and south directions. When a magnet is placed near an iron or steel piece, its property gets induced in the material, and this process is called as magnetic induction. And fourth, if a magnet is broken into two pieces, still it will have north and south poles. And some materials show the property of attraction even after removal of the magnetism. That property is called as retentivity. That is the property of a material to retain magnetism even after removal of it. Next, we have seen what are the laws of magnetism. The first law was like poles repel and unlike poles attract. Next, the second law is Coulomb's law. One pole on the other, the force of attraction or repulsion on one pole on the other is directly proportional to their pole strength and inversely proportional to the square of the distance between them. Then we have seen what is magnetic field. Some definition: it is a region around a magnet where its effect can be felt. And we have seen what are field lines or flux lines. The lines of force around a magnet. The lines of force around a magnet are called as flux lines or the field lines, and these are all the imaginary lines around a magnet. These are all the imaginary lines around a magnet. And to why these are considered? These are considered to get visualization of distribution of the flux around a magnet. And what are the properties of lines of force? They originate at the north pole and terminate on the south pole. They originate on the north pole and terminate on the south pole external to the magnet. And each line forms a closed path. Each line will form a closed path, and the lines of force will never intersect and always parallel to each other. And magnetic lines of force always prefer a path offering low opposition, and that low opposition, the opposition offered by a material to flow of lines of force, is called as reluctance. So I think this till this point everyone is clear. Now let us see what is magnetic flux. Now let us see what is magnetic flux. Let us see what is magnetic flux. So let us look at that. Magnetic flux. The total number of lines of force, the total number of lines of force existing in a particular magnetic field is called magnetic flux. The total number of flux lines or lines of force existing, the total number of flux lines or the lines of force that are existing in a particular magnetic field is called as the magnetic flux. It is denoted by It is denoted by phi, and the units of magnetic flux are Webers. The units of magnetic flux are Webers. And 1 Weber is equal to 10 power 8 flux lines or lines of force. 10 power 8 lines of force. So this is magnetic flux. So this is magnetic flux. What is magnetic flux? The total number of lines of force existing in a particular magnetic field is called as the magnetic flux. It is denoted by phi, and the units are Webers. And units are Webers, and 1 Weber is equal to 1 Weber is equal to 10 power 8 lines of force. Now let us write. Now let us see magnetic flux density. Let us see magnetic flux density. Magnetic flux density. What is magnetic flux density? We already know density. In general, density is equal to mass by volume. So what is magnetic flux density? It is denoted by B. Magnetic flux density. We have two things. One is magnetic flux density and the other one is magnetic field intensity. Magnetic flux density B, magnetic field intensity H. So magnetic flux density B, it is the flux lines per pole. It is the flux lines per unit area. Magnetic flux is flux lines per unit area. What are the units of flux? Weber. Area meter square. Therefore, units of P are Weber per meter square, or you can also write it as Tesla. You can also write it as Tesla. It is the flux lines per unit cross-sectional area. Flux lines per unit cross-sectional area is called as the magnetic flux density. It is denoted by B, and its units are Weber per meter square. Its units are Weber per meter square or Tesla. Units are Weber per meter square or Tesla. Now if you see a magnet, and let us consider magnetic flux lines around it. These are the magnetic flux lines around it. And if you have considered a cross sectional area, and the flux lines, this is north pole and this is south pole, the total number of flux lines passing through this particular area is called as the flux density. So this is the cross sectional area A, and these are the flux lines, and this is a magnet. Now let us see what is magnetic field intensity. Let us see what is magnetic field intensity. What is magnetic field intensity? So it is denoted by H. It is the strength or weakness. It is the strength or weakness of magnetic field. Strength or weakness of magnetic field is called the measure of strength or weakness of a magnetic field is called as magnetic field intensity. Is called as magnetic field intensity, and it is H is equal to Ni by L, that is ampere turn per meter. So units of H are ampere turn per meter. Ampere turn per meter. So this is magnetic field intensity. So what is magnetic field intensity? It is the measure of strength or weakness of magnetic field. It is the Measure of strength or weakness of magnetic field is called as magnetic field intensity. And now magnetic field intensity and magnetic flux density are related by permeability. What is called as permeability, which is mu, denoted by mu. So what is mu? It is permeability. What is permeability? It is ability of it is the ability of a material to allow flux lines to pass through it is called as magnetic permeability. What is magnetic permeability? It is the ability of a medium or a material to allow flux lines to pass through it. The ability of a medium to allow flux lines to pass through it is called as permeability of the material. Permeability, you have absolute permeability and relative permeability. This can be a material or a medium. So permeability in other words can also be defined as permeability in other words can also be defined as ability or ease with which the magnetic material forces the magnetic flux through a given medium. So this is permeability. Good evening, sir. Good evening, Nagesh. Welcome to Network Analysis and Transmission Lines crash course. So this is permeability. There are two types of permeabilities. There are two types of permeabilities. One is absolute permeability. Other one is relative permeability. Absolute permeability is denoted by mu naught and relative permeability is denoted by mu r. Absolute permeability by mu naught and relative permeability by mu naught. Mu absolute permeability mu naught, relative permeability mu r. We have two types of permeability. Now let us see what is relative permeability. Relative permeability. The relative permeability is defined as the ratio of flux density produced in a medium to flux density produced in free space. Under the influence of same under the influence of same magnetic field strength. This is relative permeability. That is mu r is equal to B by B naught, where B is the flux density produced in a medium and B naught is the flux density produced in free space. So this is a dimensionless quantity. This is a dimensionless quantity. It is a dimensionless quantity. That means it does not have any units. It does not have any units. What is mu r for free space? For a free space, if you say B measured is produced, flux density is B naught by B naught, which is 1. Therefore, for free space, mu r is equal to 1. For free space, mu r, relative permeability is equal to 1. Now, what is absolute permeability? Now, what is absolute permeability? Absolute permeability. Now, let us see what is absolute permeability. I think you have understood relative permeability. Now, what is absolute permeability? It is denoted by mu naught. What is absolute permeability? It is denoted by mu naught. It is the ratio of it is the ratio of magnetic flux density in a particular medium to magnetic field intensity. That is called as absolute permeability. It is denoted by mu naught is equal to V by H. Mu naught is equal to the value of absolute permeability is given by 4 pi into 10 power minus 7 Henry per meter. It is mu naught is equal to 4 pi into 10 power minus 7 Henry per meter. In this case, the magnet is placed in a free space or vacuum. In this case, the magnet is placed in a free space or vacuum or in air. So this is absolute permeability. And absolute permeability has the units of Henry per meter. Absolute permeability has the units of Henry per meter. So if you can see what is mu is equal to, what was mu is equal to? Mu is equal to B by H in one medium, and mu naught is equal to B naught by H in free space. In free space. This is in one medium. Now if you divide both the equations, you get mu by mu naught is equal to B by B naught implies but we know that B by B naught is equal to mu r. Therefore, mu by mu naught is equal to mu r implies what is mu is equal to mu naught into mu r. What is mu is equal to mu naught into mu r, where mu naught is absolute permeability and mu r is relative permeability. Mu naught is absolute permeability and mu r is relative permeability. Now let us see what is magnetomotive force. Let us see what is magnetomotive force. Like we have electromotive force, we already know the reason behind the flow of electrons. What is electromotive force? The reason behind the flow of electrons. Likewise, similarly, the force behind the production of flux is called as magnetomotive force. The force behind the MMF, the force behind the production of flux is called as MMF, magnetomotive force. It is MMF is product of N and I. It is the product of N. What is N? N is the number of turns of the magnetizing coil. N is the number of turns of the magnetizing coil, and I is the current passing through it. I is the current passing through it. Here you have to know about Ester's experiment. OESTERDS, Ester's experiment. Not only a magnet has a flux around it, Esther has told that a current carrying conductor also has some flux around it, and this current carrying is I, and these are number of turns N. And if this carries a current, the number of turns of that coil will give you the magnetomotive force. So you can say the units of magnetomotive force are mmf is equal to N into I, which is ampere turns. So ampere turn is the unit of mmf. Ampere turn is the unit of magnetomotive force. Ampere turn is the unit of magnetomotive force. Hope this is clear for you. Now let us just look what we have seen once again from the starting. So we have seen what is a magnet and its properties. So we have seen what is a magnet and what are its properties. Property like it attracts and repels, or the more attraction where it the attraction where more attraction accumulation takes place is called as the are called as the poles. Next we have seen when it is suspended freely, it aligns itself in north and south directions. And when a magnet is placed near to it, there is some property transfer, and that transfer is called as the magnetic induction. And we have seen if a magnet is broken into two pieces, it will still have north and south poles, right? So it will have north and south poles. Then we have seen some materials show the property of attraction even after removal of magnetism. That property is called as retentivity. Then we have seen the laws of magnetism, that unlike poles will attract and like poles will repel. Then the second law was force of attraction or repulsion is directly proportional to the pole strength and inversely proportional to the square of the distance between them. And magnetic field, it is the region around a magnet where its effect can be felt, is the magnetic field. Then we have seen field lines. The lines of force around a magnet are called field lines or flux lines. These are imaginary lines around a magnet, and it is taken in order to get the visualization of the distribution of flux lines around a magnet. And we have seen some properties like they originate at the north pole and terminate on the south pole external to the magnet, and each pole forms a closed path, and the lines of force will never intersect and always parallel to each other in the same direction and repel each other. And magnetic lines of force always prefer a path which offers low opposition. So that low opposition, the opposition is offered by the material to flow of lines of force is called as the reluctance. So it is maximum for the air and it is minimum for the materials like iron and steel. Then we have seen magnetic flux. The total number of lines of flux existing in the particular magnetic field is called as magnetic flux, or you can also call it as flux linkage, N into phi. And it is denoted by phi, and the units are Webers, and 1 Weber is equal to 10 power 8 lines of force. Then we have seen magnetic flux density B. It is the flux lines per unit cross sectional area. So it is flux per area Weber per meter square or Tesla. Then we have seen magnetic field intensity. It is a measure of strength or weakness of a magnetic field. So it is H is equal to Ni by L. Ampere turn per meter is the unit of H. We can also get this from Ampere circuit law. Integral H dot dl is equal to I. Integral H dot dl is equal to I. I is equal to integral H dot dl, which is Ampere's circuital law. Then we have seen permeability. It is the ability of a medium or a material to allow flux lines to pass through it, or ability of ease with which magnetic material forces the magnetic flux through a given medium. So we have two types of permeabilities, absolute and relative permeability. So relative permeability is the ratio of flux density produced in the medium to the flux density produced in the free space. So under the influence of same magnetic field strength. So we have, it is B by B naught, and it is a dimensionless quantity, and mu r is equal to 1 for free space. Then we have seen what is absolute permeability, and the value of absolute permeability as 4 pi into 10 power minus 7 Henry per meter. So magnet is placed in a free space in this case. So the units of absolute permeability are Henry per meter. Then we have seen mu is equal to B by H in any medium, and mu is equal to B naught by H in free space. So mu by mu naught, if you calculate, you will get B by B naught, but B by B naught is already, we know that it is mu r. So from this you will get mu is equal to mu naught mu r, where mu naught is the absolute permeability. Mahesh Kusma. Good evening, sir. Good evening, Mahesh Kusma. Mu r is the relative permeability of the medium. Now let us see. Then we have seen magnetomotive force, as electromotive force is responsible for reason behind the production of or flow of electrons. The force behind the production of flux is called as the magnetomotive force. It is the product of number of turns and the current being passing through it. N is the number of turns and I is the current. So mmf is equal to N into I, which is ampere turns or amperes. Now I can also define, I have also told you about the Estes experiment, wherein not only a magnet has a flux around it, also a current carrying conductor has a flux around it. And this magnetomotive force is also the work done. It is the work done in joules. The work done in joules on a unit magnetic pole in taking it once around around a closed magnetic circuit. So it is the work done on a unit magnetic pole in taking it once around a magnetic circuit is called as the magnetomotive force. Now let's look at something called as reluctance. Now let's look at reluctance. Reluctance is denoted by S. Reluctance is denoted by S. What is reluctance? We already discussed this. It is the opposition to flow of flux. It is the opposition to flow of flux. So S is directly proportional to length and inversely proportional to area. So in order to remove proportionality constant, you will take reluctance is equal to L by mu into A, where mu is the, what is mu? Mu is the permeability, and mu is equal to mu naught mu r. Now let's try to find you. Let's try to write the units of reluctance. The units of reluctance are ampere per Weber. The units of reluctance are ampere per Weber. What is reluctance is also equal to, reluctance, yes, is also equal to mmf by flux. What is mmf? Ampere turn per flux Weber. So that's how you get the units of this. So reluctance S is equal to mmf by flux, or it's also equal to reluctance is equal to L by mu into A, where S is, what is S? It is the reluctance with units ampere per Weber or ampere turn per Weber, because mmf is equal to, what is mmf is equal to? MMF is equal to N into I. So number of turns into current, ampere turns by flux. So that is reluctance. Yes. Now let us see what is permeance. Now let us see what is permeance. We also have something called permeance. What is permeance is, it is simply, you can just say, it is reciprocal of reluctance. As you have conductance for resistance, similarly you have reluctance for, sorry, permeance for reluctance. What is this permeance? It is the property of, it is the property of magnetic circuit. It is the property of magnetic circuit due to which it allows flow of, it allows flow of magnetic flux lines through it. So permeance is equal to 1 by reluctance. What is permeance is equal to 1 by reluctance. What are the units of permeance? Units of permeance are what are the units of reluctance? Reluctance units are ampere turns per Weber or ampere per Weber. So it would be Weber per ampere or Weber per ampere turn. So Weber per ampere or Weber per ampere turn are the units of permeance. So let me conclude here. We have seen what is a magnet and its properties. That was what our first topic. You just can see that we have seen what is a magnet and what are its properties. Then we have seen, if you can just go back and see this is what we have done. So this is magnet and its properties. Then we have seen laws of magnetism. Then we have seen laws of magnetism. Then we have seen what is magnetic field. Then what are lines of force or flux lines. And then we have seen magnetic flux density and also magnetic field intensity, permeability, absolute and relative permeability. And then we have seen what is permeance. Also we have seen what is MMF, magnetomotive force. If you can see what is MMF, magnetomotive force. And we have seen permeability, magnetic field strength, magnetic flux, reluctance, also reluctance. So we have also seen what is reluctance. So this is the introduction. With this knowledge you can just understand the rest of the part of magnetic circuits. Magnetic flux density B, magnetic field intensity H. Units are Weber per meter square or Tesla, and H units are ampere turn per Weber, sorry, ampere turn per meter. Ampere turn per meter. Absolute permeability Henry per meter. Relative permeability does not have no units. And permeance has the units reciprocal of reluctance. Reluctance has the units ampere per Weber or ampere turn per Weber. So this has Weber per ampere or Weber per ampere turn. Flux lines is phi. Magnetic field is the region around a magnet, and you have two laws of magnetism, and there are some properties of magnetic materials. So this is about magnetic circuits introduction. We will see much more in the next session. Thank you all. Thank you, Mahesh. Thank you, Nagesh. Thank you, Chandrakiran. Thank you, Saidulu. Thank you, Karthik, Raju, Ravi Kumar, Jayant, Simi, and Soumya, Krishnachari, and Srilata. Thank you all for joining me on this magnetic circuits. We have started a crash course, network analysis and transmission lines. We will complete this crash course with some of the topics like magnetic circuits, two ports, transients, and transmission lines. So please do join me live on at 6:30 every day and do not miss any class. Thank you all once again for joining me today. As I always tell you, we have India's number one study channels. You have so many study channels, including Unacademy semester exams. We have Creatrix Gate, Unacademy Gate, Unacademy Gate CE, Unacademy Gate Telugu, Unacademy SSC JE, Unacademy Computer Science, Unacademy Gate Questions, Unacademy Electrical Junctions, Unacademy Engineering Foundation, Unacademy Pathshala. And please do like this video, share this video, subscribe to this channel, click on this bell icon to get more notifications of my classes, and you can use my code YSK10 to get maximum discount of 10% on your Unacademy subscription. Thank you all. Thank you once again for joining me on this beautiful session on magnetic circuits.